जय हिंद स्टूडेंट्स, हाउ आर यू ऑल? आप सारे बिल्कुल ठीक ठाक हैं? आई एम वेरी श्योर यू ऑल आर fit and fine, right? In the previous session, we have discussed electric power, which is the rate of consumption of electrical energy by an electric circuit or by an electric device. We have also discussed Joule's heating effects of current, where we have studied that when the current is made to pass through a conductor, then the conductor gets heated up. And almost all the electrical appliances which we make use of our daily life, like electric iron, electric geyser, toaster, right? These all are the electrical appliances which are based on heating effects of current, right? And the rate of heat produced, that's electric power, right? So what we'll do today is we will discuss some numericals based on those topics which we have discussed earlier, right? So let's start with the first question. So the first question is, an electric heater of resistance 8 ohm draws 15 ampere from the service mains for 2 hours. Calculate the rate of heat developed. Now the rate of heat developed means amount of heat produced per unit time. And the amount of heat produced per unit time, that is known as power. So students, rate of heat developed, it means that we are supposed to determine the power, right? Heat developed per unit time, that is known as power. So in this question we are supposed to determine the value of power. So as I have told you numerous times, while dealing with numericals, first write down the information which is already given in the question. Over here, the resistance of this electric device, which is heater, is given to be 8 ohm, right? Current, it's given to be 15 ampere. Time, it's given to be 2 hours. Clear, students? So, in case we want to find out the power or the rate of heat produced in SI, the SI unit of power is watt, then we need to convert hours in seconds. So, it will be 2 hours, 1 hour is 60 minutes, each minute is equal to 60 seconds. So, it will be in seconds. Clear, students? Now, we are supposed to find out rate of heat produced, that is power. Power is the rate of heat produced, that is heat produced per unit time. This is to be determined. So what is the formula connecting these three? We have discussed the various expressions for power. Power is I square R. Power is V square by R. Power is V into I. Right? So over here, we are supposed to get the relationship between I, R and T. T won't be required as such. Right? So over here, power, it's given by, in terms of I and R, it is given by I square R. So in this numerical, this is the formula to be used. So in a single step, we will be easily able to determine the answer, right? So current, it's given to be 15. So 15 square, that is 15 into 15, and resistance, it's given to be 8. So students, it is equal to 225 multiplied by 8. So it will be 1800 watt or 1800 joule per second. Watt, as you are aware, is the SI unit of power, and 1 watt is 1 joule divided by 1 second, right? So it can also be expressed as joule per second. Clear, students? So this was a very simple question based on this direct formula. Let's proceed to the second question. We are supposed to compare the power used in the 2 ohm resistor in each of the circuits. So there are 2 cases given. So in the first case, 2 ohm resistor is connected to a 6 volt battery in series with 1 ohm. And in the second case, it is connected with a 4 volt battery in parallel with 12 ohm. So what we do is, let's discuss the first part. And wherever feasible, please draw the circuit diagram, right? It will make the numerical much more simpler. Okay. In the first case, the resistance of 2 ohm is connected to a 6 volt battery in series with 1 ohm. This is the diagram. This is 1 ohm resistor and this is 2 ohm resistor. Both are connected in series across a battery of 6 volt. This is the situation. This is the given information, right? Students, in series, the current flowing across each of the resistor is constant. So this is the current flowing. And the current flowing through each of these two resistors would be constant, right? So we are supposed to find out the power across the 2 ohm resistor. We are supposed to find out the power across the 2 ohm resistor. That's our objective. So what we'll do is, let us find out the current flowing through the 2 ohm resistor. For that, what will be the effective resistance? These two are connected in series. So net resistance would be 3 ohm. So this is the net resistance. So what will be the net current? Current would be equal to V by net resistance. So 6 by 3, it is equal to 2 ampere. So the current flowing through this circuit is 2 ampere. Students, 3 ohm is the series combination of 1 and 2 ohm. And in series, the current is constant. So current of 2 ampere must be flowing through each of these two resistors. Therefore, we have found the current flowing through 2 ohm resistor. Now consider of the question. We are supposed to find out the power used in the 2 ohm resistor, right? So 2 ohm resistor. So power across 2 ohm resistor. Now the formula for the power where current is given, it's I square R. So what is the current flowing through the 2 ohm resistor? It is 2 ampere, right? What is the value of the resistance? It's 2. So it will be 8 watt. Clear, students? So in the first case, the power used in the 2 ohm resistor when it is connected in series with 1 ohm resistor across a 6 volt battery is determined to be 8 watt. Now let's concentrate on the second part. Second part is, this 2 ohm resistor is connected to a 4 volt battery in parallel with 12 ohm. So the diagram would be like this. This is 2 ohm resistor. It is connected in parallel with another resistor of 12 ohm across a source of 4 volt battery. This is the second scenario. So here again we are supposed to find out the power dissipated across the 2 ohm resistor. Now look, these two are connected in parallel. So students, in parallel, the potential difference across the resistors connected in parallel is constant. So over here, across 12 ohm resistor, the potential difference is 4 volt. Across 2 ohm resistor, the potential difference is again 4 volt. Right? So here, resistance value is known to us and the potential difference across this resistor is known to us. So here, we can make use of the formula for power as V square by R. Right? So we need to judiciously choose the formula. Right? Read the question carefully, which informations are given, and accordingly judiciously choose the appropriate formula for the power. So here, the power across 2 ohm resistor in the second case would be, we'll make use of this particular formula. Why we are using this formula? Because V is known and R is also known, isn't it? So it's much simple. So V is 4 volt. So 4 square divided by 2. So it will be equal to 16 by 2. That is again 8 watt. So in both the cases, the power dissipation across the 2 ohm resistor is determined to be 8 watt. So the answer is, in both the cases, the power across the 2 ohm resistor is same, each being equal to 8 watt. Clear? So this was the case of the series combination and this was the case of the parallel grouping. Right? So we are done with question number 1 as well as question number 2. Third one. It's an interesting question, students. Okay, let's try to concentrate on the third question. 3 resistors, all are equal, each having resistance R. When connected in series to a source, dissipate a total power of 20 watt. Find out the power dissipated when they are connected in parallel across the same source, right? So here also it will be preferable to draw the appropriate diagram. Then it will be much more easier for me to convince you, right? So let's deal with question number 3. 3 equal resistors when connected in series, right? This will be the circuit diagram. This is the series combination of 3 equal resistors. Okay, and suppose this source, this is the source, offering potential difference V. This is the source, right? So it dissipates a total power of 20 watt. So what will be the net resistance in the case of series grouping? It will be equal to 3R. R plus R, it will be 3R. And power, net power in the case of series grouping, V is given, net resistance is given. So net power dissipation across the circuit would be V square divided by R series. So the net resistance of the entire circuit is 3R. So power of the series network of 3 equal resistances would be V square divided by 3R. Put this as equation number 1. Right? Let's concentrate the second one. Now the same 3 resistors are connected in parallel across the same source. Right? So this was the first case, this is the second case. Same 3 resistors like this. They all are connected between the same 2 points. And it is the same source. So offering potential difference B, same source. The only difference is that in the earlier case the 3 resistors were connected in series. In the latter case they are connected in parallel. So what will be the effective resistance over here? 1 by R parallel, it will be equal to 1 by R plus 1 by R plus 1 by R. So it will be equal to 3 by R. So R parallel will be equal to R by 3. Right? In both the cases V is constant. So that is why I am making use of this particular formula. Right? V in both the cases is constant. So P parallel, it would be equal to V square. Same V, same source is applied across the series combination and the same source is applied across the parallel combination. V is constant. Divided by R parallel. So it will be V square divided by R by 3. So it will be like this. Put this as equation number 2. Now what we are supposed to do is, it is given, find the power dissipated when they are connected in parallel across the same source, and in series it is given to be 20 watt. This value, it is given to be 20. It is already given. It's given to be 20. Right? So let's make use of these. So from first, V square by R is equal to 60. Therefore, from equation second, net power dissipation in the parallel network would be thrice V square by R. Thrice, and V square by R is equal to 60. So it will be equal to 180 watt. So this is the proper method of dealing with such questions. Right? So students, as I have advised you, it is always preferable to draw these circuit diagrams. Wherever feasible, draw the necessary electric circuit diagram. Right? It will make the question that much more simpler. So in series, the power dissipation was given to be 20, while in the case of parallel moving, the power dissipation is determined to be 180 watt. Right? So we are done with question number 3 as well. Let's concentrate on question number 4. It's again a very good question. It's a conceptual question basically. So let's try to attempt this one. 2 electric lamps are given and their ratings are given. This is the rating, students. 100 watt to 20 volt. It means that it can give a maximum power output of 100 watt when connected across 220 volt potential difference. Right? This is the meaning. And the other electric lamp is rated at 200 watt to 20 volt. What it means is it can give a maximum output power of 200 watt when connected across 220 volt source. Right? So these are known as the ratings of the electric device. They both have tungsten filaments of same length. It's given length of both the bulbs are constant. Show mathematically which bulb will have thicker filament. Right? So cross-sectional area of which of the 2 filaments of the bulbs will be more. Right? That is what we are supposed to find. So this is again a very, very interesting question. First and foremost, students, concentrate on this part. 220 volt, 220 volt. Right? Let's make this question simpler. Right? We need not to do superfluous mathematical calculations. Right? So here, both the lamps are operated at 220 volt. Right? So V is constant. V is constant. And we are aware of this. P is equal to V square by R. V is constant. and P equals to V square by R, and we have theoretically discussed whenever V is constant then power is inversely proportional to the resistance, or resistance is inversely proportional to the power. Clear, students? So what I mean to say is that one is of power 100 watt. There are two bulbs. This is bulb 1. This is bulb 2. One is of 100 watt. The other bulb, it is of 200 watt. So obviously, this is the first bulb, this is the second bulb, right? Its resistance is suppose R1, its resistance is suppose R2. Now resistance is inversely proportional to the power. Therefore, the resistance of the first bulb would be greater than the resistance of the second bulb. Am I clear, students? If V is constant, then power is inversely proportional to the resistance, or resistance is inversely proportional to the power. So the bulb with greater power will have lesser resistance and vice versa. So the 100 watt bulb will have more resistance as compared to the 200 watt bulb, right? This is clear. Now resistance, students, we are aware R is equal to rho L by A, right? Rho, you are aware, it is known as specific resistance or resistivity. It depends upon the nature of material of the conductor. Both the bulbs have tungsten filament, so both the cases rho would be same. Length as per the quotient is given to be constant, so length is also constant. Therefore, R is inversely proportional to area, since L is constant, right? So R is inversely proportional to the area. Therefore, 1 by A1 would be greater than 1 by A2. Am I clear? Why? Because R is inversely proportional to cross-sectional area, provided length is constant. So what do you get? A2 is greater than A1. So cross-sectional area of the second bulb is greater than the cross-sectional area of the first bulb. So the filament of the second bulb must be thicker as compared to the filament of the first one. Clear, student? So this was a very, very good question based on your theoretical concepts, right? So we are over with this question as well. Okay, let's concentrate on question number 5 then. Two conducting wires of the same material and of equal lengths and equal diameters. Okay, material, it's made of the same material, so resistivity would be same, right? Equal lengths, equal cross-section area, equal diameters, right? Are first connected in series and then in parallel across the same source. Find the ratio of the heat produced in series and parallel combinations. Okay. Two conducting wires of same material and of equal lengths of equal diameters. Now look, students. Resistance, it's given by rho L by A. A is the cross-sectional area, that is pi r square. R is the radius, so it can be written as d square by 4. D is the diameter. So if you substitute this value over here, what do you get? R is equal to rho L divided by pi d square by 4. So this is the expression for the resistance, right? Now it is given, they are of the same material, so rho is constant, right? Same length, L is constant, and same diameter. This is also same. So R is equal to constant. Am I clear? So both the conductors must be offering same resistance, right? Now, first case is when both are connected in series and then in parallel. Okay. These are the two conductors. Suppose the first conductor offers resistance R, then the second conductor will also offer resistance R, because both are of same resistance. That is what we have proved just now, right? And connected across the same source. Okay, same source. Suppose it is V, right? So what to do is find the ratio of the heat produced in series and the parallel combination. Heat produced in the series combination. Same source. V is constant. In both the cases, V is constant. So one of the formula is V square by net resistance into time. This is one of the formula. There are, students, three different expressions for the amount of heat produced across a conductor when current is passed through it. One is I square RT. The second one is V square by RT. And the third one is VIT. So these are the various expressions. One is H is equal to I square RT. Second one is H equals to V square by RT. And the third one is H is equal to VIT. So here, since in both the cases V is constant, so that is why I have made use of this particular formula, right? So these two are connected in series. So what is the effective resistance of the series circuit? So it will be 2R. So H series, it will be equal to V square divided by R net will be R plus R, that is 2R into T. Put this as equation number 1. Now as per the question, the same resistors or conductors are then connected in parallel across the same source. Okay, same two resistors. This is the second case. Now same two conductors offering the same resistance are connected in parallel across the same source. If it is offering potential difference V, it is also offering potential difference V. Source is same, right? So what will be the effective resistance over here? R net, it will be equal to R by 2. Isn't it? They are connected in parallel. So which formula is to be used? 1 by R net is equal to 1 by R plus 1 by R. Just solve it and you will get R net is equal to R by 2. So here, in the case of parallel circuit, again we will make use of this formula. V square by R into T, because V is constant in both the cases. So what you do is, it will be V square, same potential difference, same source, over net effective resistance into for the same time, right? So what do we get? V square divided by R net, it's equal to R by 2. So it will be R by 2 multiplied by T. So put this as equation number 2. We are supposed to find out the ratio of the heat produced in the series and the parallel combination. So what to do is H series divided by H parallel. This is to be determined, right? So first divided by second. What do we get is V square by 2R into T multiplied by, it will get reciprocal. So R divided by twice V square into T. V square get cancelled, T get cancelled, R get cancelled. So we will be left with 1 by 4. So the ratio is 1:4. This is the answer, right? So the ratio of the heat produced in the series and the parallel combination in the series and parallel cases is 1:4. Clear, students? Again, in this particular question, we have made use of the very basic theoretical concepts. So that's why I always keep on stressing. Once your theoretical concepts are clear, it is only then you will be able to attempt the numericals, right? So let's discuss question number 6 then. It's a relatively very simple question. It's a straightforward question. So let's try to attempt it. As per question number 6, an electric bulb is rated 220 volt and 100 watt. I have stated the meaning of this rating, right? Every electric device has got some rating. So this rating, it suggests that the electric bulb will give a power output of 100 watt when connected across a potential difference of 220 volt. So that's the meaning of this electric rating. Anyway, when it is operated on 110 volt, then find the power consumed, right? So first case, rating is given to be rating of the device. First write the rating of the device. Power is given to be 100 watt when it is connected across a potential difference of 220 volt. This is the potential difference. It may change depending upon the source, but the resistance of the device will remain same under given physical conditions, right? So whenever a rating of a device is given, then we can easily determine the resistance of that electric device. So power is given, potential difference is given. It clearly suggests that the power output of the device is 100 watt when it is connected across a source of 220 volt. So we are aware of resistance. Let's find out the resistance of this electric bulb. So what's the relationship in these three? P is equal to V square by R. We can make use of this particular relation. Therefore, resistance of the electric bulb would be V square by P. So V is 220. So 220 square, that is 220 into 220 divided by power is 100. So we get 484 ohm. Right? So this electric bulb will have a resistance of 484 ohm. Whether this electric bulb is connected across 220 volt or across 110 volt or across 50 volt or across 280 volt, the resistance of this electric bulb will remain same. Right? So by electric rating of an electric device, first try to determine the resistance of that particular electric device. Now let's proceed to the next part. When the same bulb is operated on 110 volt, now situation is resistance of the bulb is given 484 ohm. Now the potential difference across which this bulb is connected is 110 volt. Now what will be the power consumed or what will be the power output of the bulb, right? So here what we do is, again, P is to be found and V and R are given. So power output would be V square by R. This is the resistance of the electric bulb which we have calculated over here, and for this potential difference we are supposed to find out the power output. So let's substitute the value. It will be 110 multiplied by 110 divided by resistance is 484. So what we get is 12100 divided by 484. So it will be equal to 100 divided by 4. So it is equal to 25 watt. So students, the same electric bulb when connected across 220 volt source will give a power output of 100 watt. But when the same bulb is connected across 110 volt, it will give us a power output of only 25 watt. What will remain constant is the resistance of the electric device. Clear, students? So we are over with question number 6 as well. So I hope you have understood these questions. They were very, very simple. As I stated, they are based on theoretical knowledge, right? So first, before attempting these questions, do the theoretical portion very sincerely, and only then, after you are convinced of each and every theoretical concept, then only try to attempt these questions. Then it will be very, very simple for you, right? So with that note, let us finish this session, and do take very good care of yourself, and thank you. We'll continue in the next session then, right?